Title: Correlation and Regression Analyses, Understanding Relationships in Data. Introduction. Welcome to a comprehensive exploration of correlation and regression analyses. In this session, we'll delve into these essential statistical techniques used to uncover relationships and make predictions in data. Correlation analysis. Let's begin with correlation analysis, a powerful tool for assessing the strength and direction of relationships between two or more variables. It helps answer questions like, do changes in one variable affect another? Correlation coefficient. The correlation coefficient, R, quantifies the strength and direction of the relationship. It ranges from -1 to 1, where R equals 1 indicates a perfect positive relationship. R equals -1 indicates a perfect negative relationship. R equals 0 implies no linear relationship. Scatter plots. Scatterplots visually represent correlations. A positive correlation slopes upward, while a negative correlation slopes downward. Regression analysis. Moving on to regression analysis, it helps us understand how one variable, the dependent variable, changes as a result of changes in one or more independent variables. It's all about predicting outcomes. Linear regression. Linear regression is the most common form. It assumes that the relationship between variables is linear and can be expressed as y equals a plus bx, where a is the intercept, b is the slope, and x is the independent variable. Least squares method. The least squares method minimizes the sum of the squared differences between observed and predicted values. It finds the best fitting line. Multiple regression. In multiple regression, we consider multiple independent variables to predict the dependent variable. It's like adding more dimensions to the analysis. Strengths and limitations. Correlation and regression analysis have their strengths and limitations. While they can reveal relationships and make predictions, correlation does not imply causation, and regression models may not capture all complexities. Real-world applications. These techniques have a wide range of applications, from finance and economics to medicine and social sciences. They help businesses make informed decisions and scientists discover new insights. Conclusion. In conclusion, correlation and regression analysis are powerful tools in the realm of statistics. They allow us to explore and understand relationships in data, make predictions, and uncover valuable insights. Closing. If you found this exploration of correlation and regression analysis intriguing, please like and subscribe for more educational content on probability, statistics, and mathematics. Outro. Thank you for joining us today, and keep exploring the fascinating world of data analysis. Until next time, stay curious. Title: The History and Characteristics of Students' T-Distribution. Introduction. Welcome to a fascinating journey into the history and characteristics of students' T-distribution. Understanding this statistical concept is essential for making inferences about populations when we have limited data. Discovery by W.S. Gossett. Our story begins in 1908 when William Seeley Gossett, a statistician working for the Guinness Brewing Company, made a groundbreaking discovery. However, the company discouraged its employees from publishing research. To circumvent this, Gossett used the pseudonym Student when he introduced the distribution. His work revolutionized statistical methods for obtaining reliable information from samples when the population standard deviation, is unknown. Definition of student's t-variable. The student's t-distribution is named in honor of Gossett's contribution. It is defined as follows: for a sample of size, n, with a sample mean, and sample standard deviation, s, the t-variable follows a student's t-distribution with equals 1 degrees of freedom. Characteristics of the t-distribution. Let's explore the key characteristics of the t-distribution. Bell-shaped. Like the normal distribution, the t-distribution is bell-shaped. Thick tails. The tails of the t-distribution are thicker than those of the standard normal distribution. Symmetric. It is symmetric about the mean, which is 0. Degrees of freedom. The shape of the t-distribution depends on the degrees of freedom. Equals 1. Convergence. As the degrees of freedom increase, the t-distribution approaches the standard normal distribution. Understanding degrees of freedom. Degrees of freedom, represent the number of values that can vary after a statistical computation has been performed. For example, in a dataset with mean 15 and 2 unknown variables, n, we have 1 degree of freedom because can vary depending on the value of f dash. Critical value and confidence interval. Critical value, is a number such that the area under the standard normal curve between, n, backslash equals a specified confidence level. A confidence interval for backslash is an interval taken from sample data, with backslash representing the probability of producing an interval containing the true value of f dash. Example. Suppose we want a 95% confidence interval equals 0.05. We can calculate backslash as follows: equals 0.05 equals 0.95, meaning a 95% confidence interval will contain the true value of f dash. Conclusion. In conclusion, students' t-distribution is a fundamental concept in statistics, allowing us to make inferences about populations with unknown standard deviations. Gossett's pioneering work continues to shape the field of statistics. Closing. If you found this exploration of students' t-distribution interesting, please like and subscribe for more educational content on probability, statistics, and mathematics. Outro. Thank you for joining us today, and keep delving into the fascinating world of statistics. Until next time, stay curious. Title: Sampling and Sampling Distributions Explained. Introduction. Welcome to another enlightening lesson in probability and statistics. In this session, we'll unravel the concepts of sampling, sampling distributions, and the powerful central limit theorem. Random sampling. Let's start with the basics. Random sampling is the process of selecting a sample from a population in such a way that every possible sample of a fixed size has an equal chance of being chosen. It's a crucial method in statistics. Types of random sampling. There are various types of random sampling. 1. Simple random sampling. Every element in the population has an equal chance of being selected. 2. Systematic sampling. Elements are chosen at regular intervals from a list of the population. 3. Stratified sampling. The population is divided into strata, and samples are randomly selected from each stratum. 4. Cluster or area sampling. The population is divided into clusters, and some clusters are randomly selected for analysis. Parameters versus statistics. In statistics, we deal with parameters and statistics. Parameters describe a population, e.g., population mean, while statistics describe a sample, e.g., sample mean. Sampling distribution. Now let's delve into sampling distributions. A sampling distribution is the probability distribution that describes the probability of each mean of all samples with the same sample size. Mean of sampling distribution. To find the mean of the sampling distribution of means, we use this formula. Equals frac _frk _fr equals frac. Where is the sample mean and is the total number of observations? Central limit theorem. The central limit theorem is a fundamental concept. It states that as the sample size, n, increases, the sampling distribution of means approaches a normal distribution. Here are some key takeaways. 1. As n increases, the sampling distribution approaches normality. 2. The mean of the sampling distribution equals the population mean, display style. 3. The variance of the sampling distribution is the population variance divided by n. 4. The standard deviation of the sampling distribution is the population standard deviation divided by the square root of n. Practical example. Let's illustrate these concepts with an example using a population of values. Conclusion. In conclusion, understanding sampling and sampling distributions is crucial in statistics. The central limit theorem plays a pivotal role in how we analyze data and make inferences about populations. Closing. If you found this lesson informative, don't forget to like and subscribe for more educational content on probability, statistics, and mathematics. Outro. Thank you for joining us today, and remember to keep exploring the intriguing world of statistics. Until next time, stay curious. Title: Understanding the Normal Distribution and the Empirical Rule. Introduction. Welcome to another educational session on probability and statistics. Today, we'll unravel the mysteries of the normal distribution and explore the fascinating empirical rule, which provides insights into how data is spread within this distribution. The normal distribution. Let's begin with the most important continuous probability distribution, the normal distribution. Its graph, often called the normal curve, is iconic, a symmetrical, bell-shaped curve entirely above the horizontal axis. Here are some key properties. Properties of the normal curve. 1. Differentiated by mean and standard deviation. The normal distribution family is defined by two parameters, the mean and the standard deviation. 2. Highest point at mean. The peak of the curve is at the mean, which is also the median and mode. 3. Symmetry. The curve is symmetric. with the left side mirroring the right side. 4. Standard deviation impact. The standard deviation influences the curve's width and flatness. 5. Total area under the curve. The area under the curve sums up to 1, representing the entire probability. The empirical rule. Now let's dive into the empirical rule, also known as the 3 sigma rule, or the 6895 to 99.7 rule. It's a valuable guideline for understanding data spread in a normal distribution. Here's how it works. Empirical rule guidelines. About 68% of data falls within 1 standard deviation of the mean. Approximately 95% of data lies within 2 standard deviations. Nearly 99.7% of data, or almost all, falls within 3 standard deviations. Formula for scores. To calculate where a specific data point lies within a normal distribution, you can use scores. The above score measures how many standard deviations a data point is from the mean. The formula is equals frac, _FRC, equals frac. Standard normal distribution. Lastly, the standard normal distribution is a specific case of the normal distribution with a mean of 0 and a standard deviation of 1. Any normal distribution can be transformed into the standard normal distribution by converting data points to scores. Conclusion. In conclusion, the normal distribution and the empirical rule are invaluable tools in statistics. They help us understand how data is distributed and provide a framework for making predictions and drawing conclusions from data. Closing. If you found this video informative, please like and subscribe for more content on probability, statistics, and mathematics. Outro. Thanks for joining us today. And remember to keep exploring the fascinating world of probability and statistics. Until next time, stay curious. Title: Exploring Binomial and Poisson Probability Distributions. Introduction. Welcome to another informative episode of our exploration into probability and statistics. Today, we'll dive deep into 2 essential probability distributions, the binomial and the Poisson. Understanding these distributions is crucial in various fields, from business to science. Binomial distribution. Let's start with the binomial distribution. This distribution is used when you have a fixed number of trials, and each trial has 2 possible outcomes, success or failure. Think of flipping a coin, where heads might be a success and tails a failure. Binomial probability formula. The probability of getting exactly k successes in n trials follows the binomial probability formula. Px equals k equals binom k CDO pkc.c. 1p nk, where px equals k is the probability of getting k successes. Binom k represents the number of ways to choose k successes out of n trials. P is the probability of success in a single trial. 1p is the probability of failure in a single trial. Use cases of binomial distribution. The binomial distribution is commonly used in scenarios like modeling the number of successes or failures in a fixed number of trials, analyzing the outcomes of A/B testing in marketing, examining the probability of getting a certain number of defective products in a batch. Poisson distribution. Now let's move on to the Poisson distribution. This distribution is used when you're interested in the number of events that occur within a fixed interval of time or space. It's often applied to rare events. Poisson probability formula. The probability of observing k events in a Poisson distribution is given by px equals k equals frac lambda k, where px equals k is the probability of observing k events. Lambda is the average rate at which events occur in the given interval. E is the mathematical constant approximately equal to 2.71828. Use cases of Poisson distribution. The Poisson distribution finds applications in various scenarios, such as modeling the number of customer arrivals at a service center in a given hour, predicting the number of accidents at a particular intersection within a day, estimating the number of emails received in an hour. Comparison and conclusion. In summary, the binomial distribution deals with a fixed number of trials with 2 possible outcomes, while the Poisson distribution focuses on the number of events occurring in a fixed interval. Both are indispensable tools in probability and statistics, helping us make predictions and analyze real-world data. Closing. If you enjoyed this exploration of the binomial and Poisson probability distributions, please like and subscribe for more engaging content on probability and statistics. Outro. Thanks for joining us today. Keep exploring the fascinating world of mathematics and probability, and until next time, stay curious. Title: Understanding Random Variables in Probability and Statistics. Introduction. Welcome to our educational journey through the world of probability and statistics. Today, we're going to demystify a fundamental concept: random variables. Whether you're a student, researcher, or just curious about the topic, this video will help you grasp the essential concepts. Definition of random variables. So, what exactly is a random variable? In probability theory and statistics, a random variable is a variable whose value is subject to randomness or uncertainty. It represents a numerical outcome of a random experiment or process. Types of random variables. There are two main types of random variables: discrete and continuous. Discrete random variables. These take on a finite or countable number of distinct values. Think of rolling a die. The possible outcomes are 1, 2, 3, 4, 5, or 6. Continuous random variables. These can take any value within a certain range. For example, the height of individuals can be considered a continuous random variable because it can be any real number within a specified range. Probability distribution. Every random variable has a probability distribution associated with it. This distribution describes how the values of the random variable are spread out and the likelihood of each possible outcome occurring. Probability mass function (PMF) for discrete random variables. For discrete random variables, we use a probability mass function (PMF) to define the probabilities of specific outcomes. The PMF assigns a probability to each possible value of the random variable. Probability density function (PDF) for continuous random variables. In the case of continuous random variables, we use a probability density function (PDF). Unlike the PMF, which assigns probabilities to specific values, the PDF gives us the likelihood of a random variable falling within a particular range. Expectation and variance. Two crucial properties of random variables are the expectation mean and variance. Expectation mean, it represents the average value of a random variable. It's calculated by summing the products of each value and its corresponding probability, for discrete, or integrating the product of the value and PDF, for continuous. Variance, it measures the spread, or variability of a random variable's values around its mean. It quantifies how much the random variable deviates from its expected value. Applications of random variables. Random variables play a significant role in various fields, including finance, engineering, biology, and more. They are used to model uncertainty, make predictions, and solve real-world problems. Conclusion. In conclusion, random variables are fundamental to understanding probability and statistics. They allow us to model and analyze uncertainty, making them a crucial concept in various domains. If you found this video helpful, don't forget to like and subscribe for more educational content on probability and statistics. Outro. Thanks for joining us on this journey through the world of random variables. Until next time, keep exploring the fascinating world of mathematics and statistics. Title: Exploring Data Science. Definitions, Distinctions, and Tools. Introduction. Welcome back to our YouTube channel, where we dive deep into the world of data science. In today's video, we'll explore the fascinating realm of data science, its definitions, distinctions from statistics, and the essential tools of the trade. So, whether you're a budding data scientist or just curious about this field, stick around, because we've got some valuable insights for you. Definition of data science. Data science, as defined by various experts, is a multifaceted discipline that encompasses a wide range of activities. Donahoe describes it as the scientific discovery and practice that involves collecting, managing, processing, analyzing, visualizing, and interpreting vast amounts of heterogeneous data across diverse applications. Intersection of sciences. Harvard's take on data science emphasizes its position at the intersection of statistical and computational sciences, incorporating quantitative information and the theories from computer science. It's essentially about making sense of data to gain insights and make informed decisions. Data science versus statistics. Now, there's often a debate about whether data science is just a fancy term for statistics. Some argue that if you're analyzing data, you're essentially doing statistics. However, others, like Andrew Gelman, highlight that data science involves much more than statistics. It deals with databases, coding, and focuses on actionable patterns for predictive uses. Data scientists' role. Data scientists are the linchpins of data science. They are part mathematician, part computer scientist, and part trendspotter. Their role involves collecting, organizing, and transforming messy data into valuable information that can drive business decisions. Tools of the trade. To excel in this field, data scientists need a versatile skill set. Here are some essential tasks they perform. 1. Collect and transform messy data. 2. Solve business problems using data-driven techniques. 3. Work with programming languages like R, Python, and SAS. 4. Possess a solid understanding of statistics. 5. Master analytical techniques like machine learning and deep learning. 6. Identify patterns and trends in data. 7. Communicate and collaborate effectively with IT and business teams. Programming languages? Now let's take a closer look at the programming languages commonly used in data science. R. It's a free, highly extensible language for statistical computing and graphics. Python, an object-oriented, versatile language known for its clear syntax and compatibility with other languages. SAS, a commercial analytics tool with a user-friendly interface, albeit with a higher cost. Conclusion. And there you have it, a glimpse into the world of data science, from its definitions to the role of data scientists and the tools they use. If you're interested in exploring this field further, don't forget to like and subscribe for more exciting content on data science and related topics. Outro. Thanks for tuning in, and until next time, keep exploring the world of data.